S-Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
In the first part of the video, we discussed about the hard and soft acids and bases. What are acid and bases in general? How do you define them according to different theories? And what are hard acids? What are soft acids? What are hard bases and what are soft bases? We discussed different examples of these according to these classification, how they are characterized and what are the different examples. At the end, we discussed the HSAB theory, that is hard, soft, acid and base theory, according to which hard acids prefer to form bond with hard bases and soft acids prefer to form with soft bases. Like people with similar nature bond with each other and with different nature try to stay away from them. Similarly with the hard and soft acids and bases. In the second part of this video, we will be discussing about the molecular geometries. Molecular geometries is a very important topic for you to understand about the periodic properties, like how in different periodic table, in different elements are there and how they prefer to form molecules and what are the different geometries of these molecules. Welcome to S-Chan Academy, myself Dr. Garima Gaba. If you want to read more about this topic, you can refer to the book by S-Chan Publishing. The link of the ebook is given in the description box below. Let's start with the second part of the video, which says about the molecular geometry. Molecular geometry is also known as molecular structure. It is a three-dimensional structure or arrangement of atoms in a molecule. Now, when one molecule is already being formed, how its bonds are being originated or being formed in the structure, in the space, how will it occupy different space. Understanding the molecular structure of a compound can help determine the different properties like reactivity, phase of matter, magnetism, color. So that's why, because we have to find out different properties of these molecules, we should know what is the geometry of that molecule. Only then we'll be able to define or we'll be able to understand different properties of all these molecules. So bond pairs and lone pairs are taken as equivalent since all electron pairs take up some space and since all electron pairs repel each other. Previously it was said that because there are different pairs of electrons, some are lone pairs, some are bond pairs, as in some, like for example, when this molecule, suppose it is having only two atoms A and B, some electrons are being shared between both the atoms and some is only situated with this or this. So the electrons which is situated in either with, like it is only with one particular atom, then that is known as your lone pairs. That is known as lone pairs because it was only with one particular atom. And bond pairs are electrons which are at the center. So basically those pairs of electrons are helping that particular bond to be formed. Fine. So there are two different types of pairs of electrons which are being classified: bond pairs and lone pairs. Bond pairs which are helping in a bond to form and lone pairs which are situated separately. Lone means lonely, that they are not participating with other. They are very they do not want to participate with any other atom. They try to remain with only one particular atom. Repulsion is minimized if the electron pairs are oriented in space as far as possible. So this we have already discussed. For the energy to be more stable, repulsion has to be less. And for repulsion to be less, all the atoms which are coordinated or the molecule which is being formed, they try to remain as far as possible from each other so that the repulsion is less. So the number of electron pairs, if we are considering, like for example in this case 2, now in this case the shape which is there is linear, because linear is the shape which is possible only when they are only in this situation the bond angle would be 180 degree and the molecule would be linear in shape and both the bonds are as far distance apart as far as possible. When we are taking number of electron pairs as 3, so planar triangle shape is possible and the bond angle is 120 degree. This we have discussed when we were considering the coordination number. For example, in this case linear geometry would be like this. Planar triangle, that means like this in only one single plane and the angle between each would be 120 degree in one single plane. When electron pair are 4, then in that case shape is tetrahedron and the angle would be 109. So that means tetrahedron, one bond like this and 3 are in the opposite direction or out of the plane. When number of electron pairs are 5, then in that case shape would be trigonal bipyramid. This we have already discussed, like we have seen the shape over here. If we'll see the shapes like this, trigonal bipyramidal, that means 3 are in one plane, one is above the plane, one is below the plane. So if this is my A and all these are defined as B, in that case the angle between these would be 120 degree and the angle between these, like in the plane and out of the plane, would be 90 degree, right? So 120 degree in the plane and 90 degree the pyramid bonds which are being formed between the bonds which are out of the plane and which are in the plane. That's why the name is trigonal bipyramid, because 5 electron pairs are there. So 3 are in one plane, trigonal, and bipyramid because 2 bonds are out of the plane, one above the plane and one below the plane. Number of electron pair, if they are 6, in that case shape is octahedron. Octahedron shape, as we have discussed, it is very stable because all the angles are 90 degree. Like if this is my metal, 4 are situated in one particular plane and 2 are above and below the plane. So the angle, like if this is my central one and I am making 4 like this, so the angle between these would be 90 degree. Similarly, when the other one is coming out of the plane, above the plane and below the plane, in that case also the angle would be, like if I'll make this one, above the plane, below the plane, angle would again be 90 degree. So bond angle in octahedral is 90 degree for all the bonds. Like for example, in trigonal bipyramidal, there were 2 bond angles, 120 and 90 degree. Depending which atom is going on which plane, whether it is going out of the plane or in the plane, the bond angle would be 120 and 90 degree. That means 2 bond angles were there. But in the case of when a number of electron pairs are 6, so the most common shape which a molecule can have is octahedron, and in that case bond angle is 90 degree. Similarly, when number of electron pairs are 7, then the shape is pentagonal bipyramid. Like in this case 3 are there. Pentagonal means 2 more bonds are there, right? Let me just show you once more so that it becomes more clear to you. What is the pentagonal bipyramid geometry? When 5 bonds are in one plane and 2 are out of the plane. So that, as the name suggests, would be pentagonal bipyramid geometry. So when my central is like this, so I have to arrange 5 different bonds in one plane. One will be above the plane, one would be up below the plane. So the number of electron pairs are 7, or the coordination number is 7, and in this case the bond angle would be 72 degree. Because 360 divided by 5. So you can calculate, it will come to 72 degree. So bond angles of all the 5 bonds which all these bonds are being made in one single plane is 72 degree. And because it is bipyramid, that means 2 bonds are like this, one above the plane, one below the plane. So those out of the plane bonds will form 90 degree angle between themselves and between the bonds which is on the plane. Okay, so next is VSEPR theory. This we have already discussed in the previous video, but because we are discussing molecular geometry again, so it's very important for us to know about the VSEPR theory. Till now it was considered electron pairs and the lone pairs are same, but VSEPR theory, which is the full form is valence shell electron pair repulsion theory, it says shape of the molecule is determined by repulsion between all of the electron pair present in the valence shell. Repulsion between 2 lone pair is greater than the repulsion between lone pair and a bond pair, which in turn is greater than the repulsion between 2 bond pairs. As we have discussed in the last slide, there are 2 types of electron pair, bond pairs and lone pairs. Bond pairs are shared between 2 atoms, so they are situated between the two atoms. That means some part of electron is on the first one atom and some part is on the second. But lone pair is one which is lonely, which is only situated, it doesn't want to participate or doesn't want to go to the other atom. It is situated only in one atom. Those are known as lone pairs. So there are 2 types of electron pairs, lone pairs and bond pairs. Now lone pair repulsion is more. Lone pairs we represent it like this. 2 electrons are there, pair means 2. So it is on single one atom. So it is, we show like this, and the bond pair we show like this, because these are situated between the bond. They are bond pairs, that means they help in formation of bond. Lone pairs, that means only one on one particular atom. So it says, VSEPR theory says lone pair repulsion is greater than lone pair bond pair, and that is greater than between bond pair. Now we know electrons are repelling each other, but the extent of repulsion is different between these electron pairs. If we consider, or if we denote lone pair like this, now 2 lone pairs are there, so the repulsion parameter is more as compared to if there is repulsion between lone pair and bond pair, and this would again be higher than if there is a repulsion between 2 bond pairs. So 3 types of repulsion parameters would be there. Lone pair repulsion would be greater than lone pair bond pair repulsion, which in turn would be greater than bond pair repulsion. Now because bond pair and lone pairs both are present in a particular molecule, so we have to consider whether the repulsion is between lone pair bond pair, or bond pair. So the extent of repulsion will depend on the extent of interaction between these electron pairs. Magnitude of repulsion depends on the electronegativity difference as well. We have already discussed this very important property, that is electronegativity. Depending on which atom is forming a molecule and what type of electronegativity it exhibits, then it will be able to define the molecular geometry in that case. Double bond causes more repulsion than single bond. Triple bond causes more repulsion than double bond. So in doubles, like there are 3 types of bonds: single bond, double bond, triple bond. So in single bond only one sigma bond is being formed. In double bond, one sigma and one pi bond is formed, and in triple bond, one sigma and 2 pi bonds are being formed. So pi bonds are on the or above the plane, it's not on the plane. So the repulsion is more in the case of triple bond as compared to double bonds, and that is again more than as compared to your single bond. So this is how it has to be when we are considering the different molecular geometries. This we have already discussed. When we are considering number of electron pairs as 2, the geometry is possible as linear. When 3 electron pairs are there, the geometry is trigonal planar. When 4 are there, tetrahedral geometry is the most common one. When 5 electron groups are there, trigonal bipyramidal is the geometry for us, and when 6 electron groups are there, octahedral geometry is the most common one. More than this also electron groups are possible, but again because of the steric hindrance, most of the compounds which are known to us are having coordination number as 6 or having this much electron pairs, and these are the geometries for these particular electron pairs. Let's see these geometries in detail. This is a table which in general, like number of electron groups when 2, we have discussed linear. We denote this by as AX2. That means 1A is forming bond with 2X, 2 different atoms X. So the molecule is linear and the angle between them is 180 degree. Right? It's not very difficult to understand. It's the most simplest case when for example, beryllium hydride complex. So it is having 180 degree. Now the case arises when we are considering more than 2 electron pairs. For example, 3 electron pairs are there. We know in the 3, like in the previous slide we have seen that the geometry would be trigonal planar, but only when all are bond pairs. For example, if we are considering trigonal planar, we see A, X, X. This is trigonal planar geometry when in only one plane 3 bonds are there. Like if I'll see this screen as one central metal and 3 bonds are like this, so the angle would be them 120. This is the most simplest case. All are electron pair and we will be having bond angle as 120 degree. And the example of such geometry is BF3. Boron complexes usually form complexes of trigonal planar. But what happened if we are considering one lone pair also? Because we know the updated VSEPR theory said that lone pair repulsion is greater than bond pair or bond pair. So if one lone pair is there, that means if out of this bond, if 2 are bond pairs and 1 is lone pair, we differentiate bond pairs and lone pairs like this. Lone pair is like this, situated only one single atom, and bond pairs we represented by bonds because they are help in formation of the bond. Now when this types of bond are being formed, in this case the structure is a little bent because this is lone pair and this is bond pair, and it says as compared to my bond pair, this is having repulsion of lone pair bond pair, right? So according to VSEPR, lone pair bond pair repulsion is greater than that of bond pair. So what happens is it will be having more repulsion, so the angle will slightly decrease, and instead of trigonal planar geometry, it will result in a bent form of structure. It will not be planar, it will not be a planar structure anymore. Next is coordination number 4, or the number of electron groups are 4. Again tetrahedral geometries is there if we consider only the electron pairs or the bond pairs only. So in that case we will be having this tetrahedral geometry. Angle would be 109. For example, the case of methane, the most simplest case, like this is tetrahedral, no lone pair is present, we denote it like this, AX4, that means one is here and we represent it as like this. 4 bonds are there but they are not in one plane. Like if one is over here, 3 are below the plane. So the angle is like 109, for example methane. But if we are considering, these are all bond pairs, like no lone pair is present over here. But if we are considering some lone pairs, like for example one lone pair is present, so we denote it like this to represent lone pair like this. So the bond is represented like this, right? So this is suppose B and this is my lone pair. Now because of this lone pair, the geometry changes from tetrahedral to trigonal pyramidal. So we have discussed this geometry in coordination number. What happens is, this is my central atom, lone pair is situated above and 3 pyramids are formed like this. So the angle decreases. Why angle decreases? Because lone pair repel bond pair to a larger extent. Lone pair is situated only on one single atom, so it repel bond pair to a larger extent, so the bond angle decreases. If there is more repulsion from this side, so this angle will come more near to each other. So that is the reason bond angle decreases. And the example is that of ammonia. Ammonia is an example where it is having trigonal pyramidal geometry and the angle is 107. Again in the case of 4 electron pair, but 2 are lone pairs and 2 are bond pairs. So we represent it like this. And again for example in the case of water, oxygen is having 2 bond pairs and 2 hydrogen are like this. Now in this case, one lone pair repulsion is also there. We have discussed in the VSEPR theory, lone pair repulsion is the highest. It is the maximum repulsion any electron pairs feel. So repulsion is more, that means it will repel from this side, and in this, because of this repulsion, the bond angle will further decrease. So the bond angle decreases from methane to ammonia because of the presence of one lone pair, and because water is having 2 lone pairs with oxygen atom, so the bond angle will further decrease to 104. So these are very important for you to understand the different molecular geometry, how many lone pairs are there. Before going into the higher group numbers, let's see the case of this, like we have discussed, methane, ammonia and water. Methane is having, just to compare, methane is having 4 bond pairs. So the geometry is tetrahedral as shown over here. This is having tetrahedral methane. Ammonia is having 3 bond pairs and 1 lone pair. This is ammonia. This is having 3 bond pairs and 1 lone pair is with nitrogen. This is ammonia, and the geometry which will result would be trigonal pyramidal geometry. And the next is water, which are having 2 bond pairs and 2 lone pairs. So the geometry would be bent geometry because now this oxygen is having 2 lone pairs. So the bond angle decreases from methane to ammonia to water. Methane 109, ammonia 107, water 104. So the bond angle will decrease because now lone pair will repel bond pair to a greater extent. This was a bond pair, it was not repelling other bond pairs and the angle was a bit higher. But now because it is having one lone pair, it is having two lone pairs, so the bond angles decreases. So this is very important for you to understand the coordination number or the molecular geometries and what are the different bond angles which are being formed according to their geometries. Let's move ahead with the group when the number of electron groups are 5. So the basic geometry is trigonal, pyramidal, bipyramidal, but in the case when there are no lone pairs present. So this is trigonal, bipyramidal, but when number of lone pairs are 0. So that means what types of geometry it is? So basically the geometry is 3 are in one plane, and because total number has to be 5, so one is above the plane, one is below the plane. So what are the angles which we have already discussed? 120 between the bond angles which are there in a plane, and two bond angles which are out of the plane, one above the plane and one below the plane. Angle is 90 degree. Example is PCl5, PF5. So all these examples are there which shows phosphorus compounds which shows trigonal bipyramidal geometry. But now this is the case when there are no lone pairs present. When the lone pairs are present, for example one lone pair, then the geometry gets changed to seesaw. When two lone pairs are there, then the geometry is T-shaped. When three lone pairs are there, geometry changes to linear, and similarly the angle also gets changed. We'll discuss these four in the later slides, so you get the better idea how we know whether lone pairs occupy which position. Now the next is your, first let us see that examples only. So this is an example which I was talking about. Over here the electron pair are 5 in all the cases, PCl5, SF4, ClF3 and triiodide ion. So PCl5 is having 5 bond pair, no lone pair is present. So simple trigonal bipyramidal geometry is there which is shown in this structure. So 3 are on one plane, 2 are above the plane and below the plane. Angle between these are 120 degree, and between the top one and the bottom one and between the plane is 90 degree. Next is your sulfur compound which is SF4. This is having 4 bond pairs and 1 lone pair. The geometry is seesaw. So what happens in this case? Now in this case sulfur is having 1 lone pair. So this is my sulfur, it is having 1 lone pair and the bond is like this, SFF, and 2 bonds are like this, above the plane, below the plane. Why the lone pair occupy? These positions are known as equatorial position, and these two which are above the plane and below the plane are known as apical position. Which are above the plane and below the plane are known as apical position, and the one which is on the plane are known as equatorial position. So why lone pairs prefer to occupy the equatorial position? It can easily occupy these 2 positions as well, but because the angles is 120 and we already know from the VSCPR theory that lone pair repel more, the repulsion between lone pair and the bond pair is higher. So if it would have occupied this position or this position, then the angle would have been 90 degrees. So repulsion would have been greater. So just to avoid that repulsion and to minimize the system, lone pair always occupy the equatorial position. So this is the structure of my SF4 molecule. But because of this lone pair, there is a higher repulsion and the bond angle becomes like this, and the structure we say is seesaw. Normal slides which we get in the park. So it's like that, structure is somewhat tilted, not 90 degree exactly. So the structure is seesaw, and the molecule SF4 and such like that, they form seesaw structure. Next 2 molecule which we are talking about is ClF3 and triiodide ion, which are like this. ClF3 is chlorine trifluoride molecule. It are having 5 electron pairs, but 3 are bond pairs and 2 are lone pairs. Lone pairs occupy 2 of the corners and fluorine atom occupy the other 3 atoms. Before that, lone pair occupy 2 of the corners and fluorine occupy the other 3 position. Now this is my molecule. It can have either of these. 2 lone pairs are present and 3 bond pairs are present. So that means 2 lone pair can either they can come into both lone pairs in the equatorial position, or it can happen that one lone pair is in the equatorial position and other lone pair is in the apical position, in the top position. Or it can happen that all the 3 fluorine, because 3 fluorine has to be situated, 3 fluorine are in the equatorial position and both lone pairs are at the top and the bottom. This should be the stable one, because as we say, lone pair repulsion is greater, so it's most convenient for them to stay as far apart, so the maximum angle can be 180 degrees. So one lone pair can be on the top side, on the other is on the bottom side, so the angle between lone pair would be 180 degree. But the situation is this, that the angle between all these would be 90 degree. Lone pair repulsion is more, but bond pair repulsion has also to be considered. So that's why always it's a general rule, whenever lone pairs are there, they will occupy the equatorial position. So it says, as a general rule, if lone pairs occupy in a trigonal pyramidal, they will be located in equatorial position rather than the apical position. They will not prefer to be in the apical position, because apical position will share 90 degree angle with the atom which are in the plane. Again they will repel. This lone pair will repel from this side, that lone pair will repel from the other side, the bond would be disturbed. That's why they prefer to occupy the equatorial position. So this first structure would be the most stable in the case of chlorine trifluoride molecule, as we have already seen. Okay, so we were discussing about coordination number or the electron pairs as 5 and 6. So 5 we have already discussed. Like when there are 5 electron pairs, all these geometries are possible. We have discussed the example. PCl5 have the trigonal bipyramidal geometry, SF4 as seesaw, angles gets a bit bent, ClF3 T-shaped, and the triiodide is linear, because in this case 3 lone pairs are there. See, 3 lone pairs are there. So as a general rule, all lone pair will occupy equatorial position and iodide will occupy apical position. So because repulsion is same from all the sides, so angle is linear molecule will form and the angle is 180 degree. Okay, the next, because electron pair 6 or coordination number 6 is very common, octahedral geometry is the most stable geometry. And whenever we have AX6, that means no lone pairs are there, then octahedral geometry is there and 90 degree angle is there. So for example, if I'll consider the example of SF6, then octahedral complex will be formed. How octahedral complexes are there? That is easy for you to know. Sulfur is there and 4 oxygen are in one plane, one above the plane, one below the plane. So when all sulfur, 4 fluorine are there, the bond angle between them would be 90 degree, and the bond angle between the bonds which are out of the plane and between this would again be 90 degree. So these angles are also 90 degree. That's why all bonds are showing the bond angle as 90 degree. But if we have the lone pairs, we have to consider their repulsions as well. So if one lone pair is there, then the geometry is square pyramidal. What happens? For example, if we consider the case or the example of bromine. So bromine is having one lone pair and 5 fluorine. So 4 fluorine would be in one plane and 1 is below the plane. And because the lone pair will repel these electrons to a greater extent, so the bond angle changes from 90 degree to 84 degree. Why? Because of the repulsion of the lone pair. Lone pair is there on the bromine, so it needs more space towards bromine. So it will repel other bond angles to a greater extent. Similarly, now when we have 2 lone pairs, now you will see now because the angle decreases because of the presence of lone pair. Now in this case, there are 2 lone pairs, but still the angle is getting increased. Reason is xenon complex. All fluorine is in one plane and one lone pair is on the top side, one lone pair is on the bottom side. So whatever repulsion is being faced from the top side, it is being overcome by from the bottom side. So again the angle would be 90 degree between these, and the geometry which is there in these complexes is square planar. It is also very symmetrical geometry, and it is found in many of the compounds. So the bond angle in each of the cases is 90 degree, and the geometry is there is square planar. So these types of geometry is very symmetrical and very common when 4 coordination number is there or when 2 lone pairs are there. So we have already discussed over here like different geometries. So example we have discussed like in the case of coordination number 4 or 4 electron pairs are there. So ammonia, methane and water are there. Depending on the which lone pairs are there, their geometry gets changed. Similarly, we discussed second example where electron pairs are 5. PCl5, SF4, depending on what lone pairs like 5 bond pairs, 4 bond pairs and 1 lone pairs, different geometries we observe. Similarly over here as a general rule we found out that whenever there is a lone pair in trigonal bipyramid geometry, it will always occupy equatorial position and not apical position, because apical position will face 90 degree angle with other angle bonds in the plane and they will have the more repulsion. And in the last we discussed about the different linear complexes as well, which would be the case of triiodide ion, that is this one which is having 3 electron pairs. So the bond angle would be 180 degree. 3 as a general rule we discussed that lone pairs will be on the equatorial position and 2 iodide will be on the apical position and the bond angle would be 180 degree. So linear molecule is being formed. So in this second part of the video, we discussed different molecular geometries. So previously it was said that all electron pairs repel to a similar extent, but according to VSCPR, we came to know that there are 2 electron pairs, lone pair and bond pair, and their repulsions are different. Bond pair repulsion is different from the lone pair repulsion. So we should know what how many number of lone pairs are there, how many number of bond pairs are there. Then only we are able to know what types of geometry a molecule will have. And according to the geometry, we will be able to know different properties, what are the bond angles, what are the bond strength and so on. And if you want to read more about this topic, then you can refer to the book by S. Publishing. Please share, like and subscribe to our videos and press the bell icon so that you can get all the notification from S. Academy.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.